In this video, we're going to talk about a technique that can be used to solve systems of differential equations. The idea is to rewrite the system of equations so that you can use the algebraic technique of method of elimination that we learned in algebra for solving systems of algebraic equations. And the thing that we're going to use to rewrite our differential equations so that we can use this technique is we're going to use the differential operator, which is called capital D. Capital D is just another way to express the derivative of a function. We've got about 17 million ways to represent the derivative of a function, and here is one more. For example, if you want to write the derivative of y with respect to t, we have the notation dy dt. We also have the notation y prime of t. But now we're going to introduce the notation capital D of y. Capital D, the differential operator as applied to y. The differential operator can also be used to represent higher order derivatives. We have d2y over dt2 to represent the second derivative of y with respect to its variable t. And using the differential operator, we would write this as d twice d squared applied to y. Now we can also use the differential operator to express things like y prime plus 3y. Y prime is the same thing as dy. So if I rewrite y prime using the differential operator, and then in some sense factor out y, then we can rewrite this expression as the quantity d plus 3 times y. So now that we've established what the differential operator represents, let's outline the general technique that we'll use to solve a system of differential equations using the method of elimination. The first thing that we do is we bring all the dependent variables, all the output variables, to one side, usually the left side, of the equations in our system. And then we rewrite all the derivatives using the differential operator. Once that's done, we combine like terms. What I mean by that is, if you have something like dy plus 3y, combine that into d plus 3 times y. That way, there's only one copy of y. Now, once that happens, you're going to want to apply multiplied constants and differential operators to one or both of the equations to get a so-called canceling pair. For example, to get something like 3 times d minus 2y in the first equation and something like negative 3d minus 2y in the second equation, you want two terms in the equations which are complete opposites of each other, which would cancel out if you added them together. And then you're going to add these equations together so that that canceling pair will vanish. Now, once you've eliminated that canceling pair, you should be left with a single equation with only one output variable. So solve that equation to figure out the value of that output variable. And then use the result of 6 to find the value of the other output variable. Extremely similar to the method of elimination as used in algebra to solve systems of equations. So let me go ahead and demonstrate the method in an example. First, an abstract example. Let's go ahead and solve the system of equations dx dt is equal to negative y plus t. dy dt, I say, is equal to x minus t. So I'm going to start by pulling all the output variables to one side. Now, since the derivative of x is being taken with respect to t, and the derivative of y is being taken with respect to t, then t is the input variable of both x and y. So I'm going to pull all the y's and all the x's to the left side, and I'm going to leave t on the right side. So now I'm going to rewrite this using the differential operator. So instead of having dx dt, I'm going to write this as d applied to x. And in the second equation, instead of dy dt, I'm going to write this as d applied to y. Noting that capital D is shorthand for the derivative with respect to the independent variable time. Now, as I've written this system, I've just rearranged the terms a little bit so that the x's are vertically stacked and the y's are vertically stacked. I find that it just makes it a little bit easier to do the next step if the x's and y's are aligned. So now my objective is to manufacture a canceling pair, to manufacture two terms which are identical but opposite in our two equations. Now my attention is drawn to the x terms actually. If the second x term just had a d attached to it, then the terms would be identical but opposite. So I'm going to apply the differential operator to the second equation to manufacture a canceling pair in the x's column. So my first equation is unchanged. I didn't do anything to that. But in the second equation, what do I have? I have the differential operator being applied to x. I have the differential operator being applied to dy. So now I have two differential operators applied to y. And I have the differential operator applied to negative t. So the derivative of negative t with respect to t is equal to minus 1. Don't forget to apply the differential operator on the far right side. So now that I've created this canceling pair, I can add these two equations together. And when I add them together, dx and negative dx will completely cancel out. And I'm left with d squared y plus y is equal to t minus 1. In more familiar notation, this would be y double prime plus y is equal to t minus 1. But this is a second order non-homogeneous differential equation, the likes of which we've solved hundreds of millions of times by now. So let's go ahead and solve this equation by the usual means. First, we're going to need to find the complementary solution. So if I set y double prime plus y equal to 0, and guess the solution of exponential form, I gotta be careful, that would be e to the rt, since t is the independent variable. Then I get the auxiliary equation r squared plus 1 equals 0, So I get the complementary solution C1 cosine plus C2 sine. Now let me guess a particular solution of a form which is similar to the function that I have on the far right side of my differential equation. The function on the far right side is linear, is a polynomial of degree 1. So let me guess a solution which is of the form polynomial of degree 1. And be careful, once again, we have to remember our input variable is t and not x. X is another separate output variable. Now if I plug that into our differential equation, y double prime is just 0. So I'm left with at plus b, our y function, is equal to t minus 1. So that's super straightforward. It looks like y sub p is exactly the same thing as our function on the far right side. Nice. So with that, we now have a general solution for y. The general solution for y is that y is equal to our complementary solution plus our particular solution. But we're not done yet. It still remains for us to find the other output variable, namely x itself. And in order to do that, I'm going to use one of the equations from our system. In particular, notice that this second equation, I'm going to extract this one actually, because in this equation we have just x, we don't have the derivative of x, and just x is what we're looking for. So in other words, x itself, after some rearranging, is the same thing as the derivative of y with respect to time plus t. Now if I take the derivative of the function that I found in the previous step, I get c1 negative times sine t plus c2 cosine t plus 1. And therefore, if I add t to that, then that will be the formula for my x in the system. So these two results together are the solution to the system of differential equations. Let's apply it to the system that we obtained at the end of yesterday's video, which was for mixtures in multiple tanks. Now, we already set up the differential equation which represents this system, so let me go ahead and copy paste it. So now let's go ahead and solve this system of equations. The first thing that I'm going to do is I'm going to bring all of our output variables to the left side. And while I'm at it, I'm just going to go ahead and rewrite a few things using differential notation. So not the derivative of xa with respect to t, but simply dxa. I'm going to pull over the 2 over 25 xa, and I'm going to pull over the x sub b over 50. Likewise, I'm going to pull the 2xa over 25 to the left side in the second equation. I'm going to rewrite dxb dt as the differential operator applied to xb. And I'm going to pull over that final term plus 2xb over 25. Now the fractions are starting to get on my nerves, so I'm just going to go ahead and hit everything with a 50 for simplicity's sake. And so we have 50 dxa plus 4xa minus xb is equal to 0, minus 4xa plus 50d xb minus 4 plus 4 xb equals 0. Now that I've done that, I'm going to combine like terms. So instead of having two terms containing xa, I'm going to factor out that xa, leaving 50 times d plus 4 quantity times xa. And then we have negative 4xa, and similarly 50d plus 4 x sub b. Once again, my goal is to manufacture a canceling pair. And it's not quite as simple as it was before. When in doubt, you can always do it in the most aggressive way. You can take the coefficient of xa in the second equation and use it to multiply the first equation. And you can take the coefficient in the first equation and use it exactly and apply it to equation number 2. So let's go ahead and do that carefully. Equation number 1 gets an extra copy of 4. Equation number 2 gets an extra copy of 50d plus 4. Now that we've manufactured this canceling pair, these two terms identical but opposite, now we can go ahead and add these two equations together. And we get 50d plus 4, 50d plus 4, x sub b, minus the 4x sub b from the first equation, altogether equal to 0. Now let's simplify this and rewrite this in a more standardized format. If I quote-unquote FOIL this expression on the far left side, then I get 2500 d squared. I guess this is 400 times d from the two outer and inner terms, plus 16. And multiplying that through, we can rewrite this as 2500 x sub b second derivative plus 400 x sub b first derivative plus 16 minus 4, so plus 12, x sub b with no derivatives equals 0. I've gone ahead and eliminated that common factor of 4 in all three terms, but there doesn't seem to be much else that can actually be done that would be meaningful. So now let's go ahead and guess a solution of the form exponential, which gives us the auxiliary equation 625r squared plus 100 times r plus 3 is equal to 0. And from the quadratic formula,
x is equal to negative b plus or minus the square root.
Alright, the calculator reveals that the solutions are negative 1 over 25 and negative 3 over 25. So therefore the solution x sub b is given by c1 e to the negative 1 over 25 times t plus c2 e to the negative 3 over 25 times t. We don't have to worry about a particular equation because the differential equation that we got in this problem was homogeneous. So now it really just remains to find x sub a, the amount of salt in tank number A at any given moment. So I'm going to go back to my system of differential equations, and it looks like the easiest one to use to find x sub a would probably be this one. This equation only contains one copy of x sub a and not the derivative x sub a, just x sub a itself. So this looks like the easiest equation to use to find the value of x sub a. So if we substitute the formula that we just found for x sub b, negative 4x sub a plus 50 times the derivative of x sub b, which, looking at x sub b, looks like it will be negative c1 over 25, e to the negative t over 25. And then the derivative of the second term would be similar, except with a 3. Multiplied by 4 times the original equation x sub b, oh, almost forgot the over 25 here. Now to rearrange this expression to find the value of x sub a, we have 4xa, I've moved it to the right side, multiply through by 50, so we get negative 2c1 minus 6c2 and in the bottom we have plus 4 c1 e to the negative 2 e to the negative t over 25 plus 4 c2 e to the negative 3t over 25. So if we combine these like terms and divide by the 4 on the right side, we get that x sub a as a function of time is equal to 1/2 c1 e to the negative t over 25, and then minus 1/2 c2 e to the negative 3t over 25. Now to finish this problem, we can actually determine the values of c1 and c2 using the information that's given to us about the amount of salt in the tank called A and the tank called B initially. In the problem, we were told that initially tank A contains 25 pounds of salt, and initially tank B contains pure water. So translating those into mathematical initial conditions, we would say that xa of 0 is equal to 25 and xb of 0 is equal to 0. Now if I plug 0 into xa, I get 1/2 c1 minus 1/2 c2 is equal to the 25 pounds of salt that was in tank number A initially. If I plug 0 into xb, I get c1 plus c2 is equal to 0, the amount of pounds of salt that was in tank B initially. So this means that c2 and c1 are opposite, and if I plug that into equation number 1, 1/2 c1 plus 1/2 c1 is 25, therefore c1 is 25, and therefore c2 is the opposite of that, minus 25. All that we have to do is plug the values of c1 and c2 that we calculated into the equations for xa and xb. This concludes today's material. We learned a technique called the method of elimination that could be used to solve a system of differential equations. Then we applied it to the particular problem of the mixing of liquids into connected tanks.